Hi, we are from Group C. The topic will be discussed is partial differential equation in the case of fluid flow wave equation. So, what is partial differential equation? Partial differential equation is a mathematical equation that involves two or more independent variables and unknown function and partial derivative of the unknown function with respect to the independent variable. Following are some partial derivatives of U. And here are some examples of PDE. We have 5 examples. So, we have 2 methods to solve PDE. The first one is separation of variable, and the second one is the element method.
My name is THAQIF, and today I'm going to talk about what are the methods used to solve partial differential equations. The answer is we have 2 methods, which is first is method of separation of variable, which is known as MSB. MSB is common method to solve PDE problem. The idea is to reduce the problem from solving PDE to solving 2 ODEs. For example, let's use this equation. By using the idea of MSB, we want to find a solution in the form like this: U equal to x as tt, which x as tt is some function of xt respectively. So by separating the variable x and t, we can solve for 2 ODE instead of PDE. So how it works, this is the step by step how it works. So after undergo the step by step, after that we can proceed by applying the boundary condition and initial condition to find the solution. So second is the Lambert method. This method is used of the swiftly for the wave equation for infinite boundaries and boundaries that are far away and not include the wavelength. Let's use this wave equation for example. Firstly, we need to know the subject to the boundary conditions, which is this, and then we just need to use the D'Alembert formula, and then we can solve the equation. So next we are going to talk about what are the applications of partial differential equations. So as we all know, there are several applications of PDE. So this is some of them. But in this video, and our group has already chosen about application of fluid flow. So we are going to do the application of fluid flow. This is some basic information that you need to know in order to solve the application of fluid flow.
A scientist wants to study the motion of water wave, but how should he do so? He can use the wave equation, which is delta square u over delta t square equals c square delta square u over delta x square, which is a partial differential equation, to study the water wave. The scientist set out a water flow experiment in his lab. The water wave or wavelength L is fastened at its ends x equal to 0 and x equal to L is released from its horizontal position with initial velocity gx, given as gx is equal to x when x is in between 0 and L over 3, and gx is equal to 0 when x is in between L over 3 and L. To help him solve the wave equation, determine the displacement of the wave at any instant.
So, hi, I'm Danzi. I would like to solve this question now. So, to determine the displacement of the wave at any instant. So, this is the solution for wave equations, and from this wave equation, what we want to find is the AN and BN and substitute into this. Okay, so from this question, this is released, the water wave is released from the horizontal position. So this means that the AN is equal to 0. So after this, the AN equal to 0, the solution for the equations, it will become this. Okay, because the AN is equal to 0. So the next thing we need to find is the BN. So BN is equal to 2 over n by c and L0. So the gx is here. Okay, so from 0 to L, okay, let me change the L. It becomes gx sine n by x over L dx. And then next thing we continue to do, and then we know that from this, okay, from this part the GL actually the range can be separated. So how to separate it? It will become 0, 1, 2, 1 over 3 else, and then the x sine n by x over l dx plus 1 over 3 l to l. So this from this is 0, and yeah, continue to write. And then anything integrate 0 is 0, so we continues to write like this. Okay, the next thing we need to do is the tabular methods. So differentiate, integrate, and then x, 1 and zeros, and this is the sine n by x over l, and we integrate it, it will become this. Integrate it again, and it will become this. So positive, negative, positive, and the arrow. Okay, so we have successful to integrate this. Okay, later we write down the integrations, and then this negative and negative, it will become positive, and yeah, like that. So very simple. And next thing we need to do is we need to substitute the value into it. So after we substitute the 1 over 3 l into it, it will become 1l squared over 3n pi cos, and we substitute into x, and this will become n pi over 3 plus l squared n squared pi squared sine n pi over 3. So until this step, we have successful to find the bn's. Okay, we have completed the bn's. So for the final solution, what we need to do is we need to substitute the bn's into this. Okay, you can see this formula. So uxt equal to, so now here, okay, we have some place. Okay, then we continue to substitute the bn into it. Cos n by 3 n squared by square sine n pi over 3, and then don't forget that for the formulas you have these two signs here. So continue to write now, and this is our final solution for this question.
Hi, I'm Ying. I'm going to explain about the problem statement 2 application of wave equation in biomechanics field. Nowadays, biomechanics is one of the forerunners in the field of cardiovascular to provide effective predictions and treatments. In biomechanics, the study of biofluid mechanics is important due to its ability to model biological phenomena. Partial differential equations can be applied to reveal the mathematical models of blood flows in the arteries in order to demonstrate the relevance and applications of modeling biological phenomena. By applying the principles of conservation of mass and the conservation of momentum to retrieve the Euler's continuity equation in a series of mathematical manipulations, the wave equations for the flow of blood through artery or capillary are obtained as below. S is the cross-sectional area of artery or capillary, V is velocity, and P is the pressure inside the artery or capillary. So, how can a biomechanic solve the equations if he has the following initial values?
Now I would like to continue to solve this question. So from this question given, there has two equations we need to find. So I will separate it into two parts. So let us find this first. So I will use the D'Alembert method to solve it. So from this method, we need to find ff and gx. Fx will refer to the v, the velocity, e power of x, and the gx will refer to the partial differentiations. And now from this equation we can find that there are three things we need to find. So how to find these three things? So I would like going to show you. So f x minus ct is equal to this. yeah, this come from this part, and then the next thing is E plus CT. So this also come from this part. After we get this, we continue to substitute it back into the solutions. So E minus CT plus EX plus CT. Okay, and then this plus 1 over 2C. So this is a integration here. Okay, we continues to this we can substitute it out, becomes ECT plus ECT. E minus CT. Okay, and then this bracket I changed a little bit. Okay, after this, and we integrate this, it will become tangents, the inverse tangents S plus CT S minus CT. Okay, so for this part, we know that this can be simplified into the what we call the hyperbolic functions cos CT. Okay, and then this we continue to substitute the values into the from the tangents, and we will get this. So this is at all for the part 1. So we have successfully to find the equation of the part 1. Continue to solve the equation for the second part. So the second part is a P. Okay, so from this we know that Px is 1, so the Fx is 1, and the Gx is refer to the partial differentiations. And then now we continue to use the same way to solve it. So no matter this is negative CT or plus minus CT or plus CT, it will become 1. So we can directly substitute it, become 1 plus 1 plus 1 over 2C, and same thing we need to using the integration here. So this will become 1 plus 2C. After we integrate the hyperbolic secant x, we will become hyperbolic tangent x. So we need to substitute the value into it. Minus tangents, yeah. So this is the final solution for the second equation.
Now, we've finally reached the end of the video, but let's see the summary a bit, shall we? Previously, we have learned the ordinary differential equations, and now the partial differential equations. To make it simple, partial differential equations are used to mathematically formulate and thus aid the solution of physical and other problems involving functions of several variables. In this video case, we are solving the application of wave equations in water flow and biomechanics. Other examples where PDE can be applied are propagation of heat or sound, elasticity, electrostatics, and electrodynamics, just as mentioned in the beginning of the video. Despite it is way more difficult than ordinary differential equation, where we need to deal more independent variables, we can still manage to solve these problems by using suitable methods. We also notice that this application may apply it in physics and engineering as well. Lastly, these are our references for making the video. Thank you for watching.